Recent studies have shown that haptic sensing can be used effectively for legged robot localization in extreme scenarios where vision sensors might fail, such as mines and sewers. However, existing haptic sensing is used mainly for supervised classification with handcrafted terrain classes. This is a significant limitation in real-world applications, where prior labeling is often impractical. This paper proposes a novel haptic localization system based on a fully unsupervised terrain representation learned solely from the four-stroke sensors at the quadruped robot feet. Given a quadruped robot, we wish to blindly localize the robot's base against a prior map using a sequential Monte Carlo method, given a source of odometry and the four-stroke signals measured at the feet. It is assumed that the robot's low drift or drift-free pose estimate is available to build the prior map. We use the Animal B300 equipped with the sensorized feet and the internal odometry estimator. The odometry from the robot is fused with the latent vector from the encoder using a sparse latent map as a prior. Optionally, a geometric map can also be used for increased accuracy. For the encoding, we propose an architecture called Improved Autoencoder, consisting of three types of blocks: convolutional, recurrent, and fully connected. This combination of blocks extracts high-level feature representation of the time series signals and can process variable length data. The sparse map was generated from steps recorded prior to the localization using the sensorized feed. Whenever Animal's state estimator detected contact between the ground and a foot, 160 samples of 3-axis force and 3-axis torque signals were collected from a foot. Then, the signals were processed by the encoding algorithm, resulting in latent vectors. This resulted in a database mapping the global position of each footstep and the corresponding latent vector. To store the encoded signals from this phase, we defined a data structure called latent map. The latent map stores the sparse information about the encoded representation of tactile signals and their position in a Euclidean space. The sequential Monte Carlo algorithm was evaluated over an area containing flat terrain with 2 ramps covered by 8 different terrain types. The ground through robot movement was recorded from the external motion capture system, providing pulses at 100 Hz. The reference map for the geometric component was captured with a sub-centimeter accurate Sarvik-grade 3D laser scanner. The visual analysis of results reveals that the method is effective at decreasing the accumulated drift of the internal odometry of the robot. This is true both when crossing boundaries between terrain classes and also observed while walking over long stretches of the same terrain class. The latter benefit is a direct result of using unsupervised terrain representations instead of explicit classes. In this work, we propose to utilize the unsupervised compressed force-torque signals directly in haptic localization framework for routine inspection tasks.